Welcome to the Explainer. Today we're diving into a seriously high-stakes engineering reality. It's about one of the absolutely crucial safety mechanisms in modern EVs, the dual motor controller firmware version mismatch. Technically, it's known as Diagnostic Trouble Code, or DTC, U0311. Now listen, this isn't your everyday IT glitch where an app just freezes up and you reboot your phone. No way. In the world of multi-source power control, a software mismatch can literally lead to unexpected torque surges or a total system control failure. That elevates this to an ASIL D safety goal, which is the absolute highest classification of risk in automotive engineering. It's really fascinating to see how this intersection of physical hardware and digital code is secured, so let's get into it.
So picture this, right? You're in an electric vehicle, cruising down the highway, and the internal motors are screaming along at a blistering 12,000 RPM. Out of nowhere, a tiny data discrepancy hits the controller. What actually happens when a dual-motor controller just forgets its own physical parameters at that insane speed? Well, the result isn't just a friendly dashboard warning light. Without instant detection and intervention, you could be looking at runaway torque, an immediate loss of vehicle control, and quite literally the catastrophic physical destruction of the powertrain. The stakes out there on the highway are absolute, which is exactly why engineering these systems to instantly recognize their own state is a matter of life and death.
Okay, let's look at our roadmap for today. We'll start with firmware fault root causes, then architecture and diagnostics, move into DFMEA key design preventions, look at PFMEA key process controls, and finally, wrap up with DVP and R production validation.
Section 1. Firmware fault root causes.
To build a solid defense, we kind of need to understand the enemy first, right? So let's look at the four main culprits that can trigger a U0311 fault and totally compromise a multi-core vehicle control system. First up, we've got low-voltage power sags, basically brownouts that happen during firmware flashing. Second is a hardware-software mismatch. Let's say a technician replaces a motor, but totally skips the commutation offset learning step. The system might miscalculate angles by, say, 45 degrees, inducing a massive power surge that literally melts the silicon carbide power modules in a fraction of a second. It's wild. Third, communication database drift. This is where tiny version differences between the vehicle control unit, battery management system, and power control system cause data to shift around, turning your safe torque limits into completely random, dangerous commands. And finally, secure boot failures. Think cosmic rays randomly flipping a bit in memory, or unauthorized firmware bypassing the initial safety checks entirely.
A really great example of how things go wrong is a torn right. Now that might sound like a purely digital problem, but it's actually a highly physical failure mode. Imagine an over-the-air update actively writing megabytes of code to the flash memory. Suddenly, a totally unrelated 12-volt relay clicks on somewhere else in the car, and it drops the voltage supply just slightly below the critical threshold. That tiny transient voltage drop leaves the memory storage cells electrically unsaturated. The system might actually think the write was completely fine, but upon reboot, boom, it triggers uncorrectable multi-bit error correction code failures. The data is literally torn, completely corrupting the vehicle's operating code.
Section 2. Architecture and co-diagnostics.
Knowing how easily a voltage drop or a skipped calibration can corrupt this code, how on earth do we build a system to catch these threats before the high-voltage contactor even closes? Well, a rapid dynamic handshake takes place. The battery management system, the vehicle control unit, and the power control system all rapidly fire off encrypted version tokens to one another. The system instantly decrypts and compares the hash values. And here's the crazy part. This entire 3-round diagnostic handshake has to execute perfectly within a brutally tight 20-millisecond window. If there's even a single character out of place, or if they miss that tiny window, the system immediately throws the DTC U0311 code and totally blocks high voltage from engaging.
Now you might be wondering, what happens if an over-the-air update fails mid-download? The way automotive engineers solve this is just brilliant. They use a dual-zone flash architecture. It's essentially a digital time machine. Bank A stores the historical, healthy software version. Then, during an update, 100% of the new firmware gets written into a completely separate Bank B. Bank B is then put through rigorous SHA-256 cryptographic hashes and error correction code checks. If any of those checks fail, like from one of those torn writes we just talked about, the system's boot pointer automatically redirects right back to Bank A. It instantly rolls back to the safe version, totally preventing the vehicle from getting bricked.
Section 3. DFMEA Key Design Preventions.
We've seen the architecture, but how do we engineer the physical hardware from day one to survive these faults? This brilliantly illustrates how hardware actively protects software. Instead of relying purely on software to notice a brownout, engineers design a precision hardware hard block.
If the voltage drops below exactly 4.5 volts for the analog rail or 3.0 volts for the digital one, a physical circuit literally cuts off the write enable pin to the flash memory. It stops the writing process cold, totally neutralizing the risk of a torn write. We also see things like dual redundancy for boot headers, read-only signature blocks to prevent communication drift, and a wear-leveling algorithm that ensures the flash memory can endure over 100,000 write cycles. That means the car can handle routine updates for decades without breaking a sweat.
Section 4. PFMEA Key Process Controls.
Now, it's one thing to design a perfect system on a computer screen, but manufacturing thousands of them flawlessly, that's a whole different ballgame. When we talk about ASIL D safety standards in manufacturing, we are dealing in absolutes, 100%. That means mandatory unique ID checks for every single board. It means 100% completion of rotor offset learning locks, and total 3D X-ray screening for every single unit. There is absolutely no sampling, no good enough on this assembly line. Every single controller must pass every single gate, full stop.
Let's see how this creates a completely uncompromising factory ecosystem. The Manufacturing Execution System, or MES, is the ultimate gatekeeper. Say a firmware flash happens, but the unique ID and SHA-256 checksum don't perfectly match the factory database. The system physically stops the line. It literally blocks the machine from printing the serial number label. During end-of-line testing, if dynamic rotor calibration fails, it triggers a physical lockout right then and there. And for the circuit boards themselves, advanced 3D acoustic and X-ray scanners make sure total voiding in the solder joints is under 5%, with no single void larger than 1%. This ensures that thermal vibration won't randomly break a connection and corrupt your data years down the road.
Section 5. DVP and PR Production Validation.
So, we've designed it securely and manufactured it perfectly. But before this controller ever sees a public road, it has to survive the absolute climax of the engineering process, the extreme torture tests. This is where engineers actively try to destroy the unit. In the OTA power drop test, they wait until an update is exactly 50% complete, literally its most vulnerable moment, and brutally cut the power down to 5 volts. The unit has to detect the torn write with 100% accuracy and roll back in under 500 milliseconds. Then comes the physical abuse. They shake it with violent 35 meters per second squared shocks while rapidly swinging the temperature from a freezing -40 all the way to a boiling 125 degrees Celsius, demanding zero data loss. Finally, on the hardware and the loop bench, while the motor is screaming at 12,000 RPM under full load, engineers maliciously inject corrupt code. The system gets exactly 100 milliseconds to catch the error and save the car.
Now, if an error is caught while you're actually driving at highway speeds, the car can't just shut the motors off completely, right? That would cause a massive, dangerous loss of power in fast traffic. Instead, it triggers the ASIL D limp home mode. The system safely and instantly scales back to a maximum of 30% torque and restricts your top speed to 40 kilometers per hour. This lets the driver safely navigate over to the shoulder, maintaining physical control over a digitally compromised machine. You see, safety is just as much about how you fail as it is about preventing the failure in the first place.
We've seen the incredible lengths automotive engineers go just to synchronize hardware and software. We can physically block voltage drops, use cryptographic tokens in milliseconds, and survive extreme torture tests. But as cars become even more deeply integrated with cloud computing and AI, it brings up a really fascinating thought. If we can secure our hardware against literal cosmic rays and factory brownouts today, what is the next frontier for over-the-air update safety tomorrow? It really makes you wonder, doesn't it? Thank you so much for joining this explainer, and keep asking the big questions.